Hi all, let's going to see about tree ADT. So tree is a non-linear data structure compared to arrays, linked list, stacks and queues which are linear data structures. So tree can be empty with nodes, or a tree is a structure consisting of one node called the root and zero or one or more subtrees. So trees are hierarchical data structures. So this is the general representation of a tree. So we have a root node, then parent node, child node. The leaf node is the last node. So root node will be at level 0. Next, its children, it goes with level 1, level 2 and level 3. So the node with no more classifications, or the last node is called as the leaf node. Next, tree terminologies. So these are some of the terms to be known before going to see about trees. So first is path. So path refers to the sequence of nodes along the edges of a tree. So root. The root at the top of the tree, the node at the top of the tree is called root. There is only one root per tree and one path from root node to any node. So parent. Any node except the root node has one edge upward to a node called parent. Next one is child node. The node below a given node connected by its edge downward is called its child node. Next is the leaf node. The node which does not have any child node is called the leaf node. Like subtree. Subtree represents the descendants of a node. Visiting is also called traversing. So visiting refers to checking the value of a node when control is on the node. Traversing. Traversing means passing through nodes in a specific order. Next, node. A node is an entity that contains a key or value and pointers to its child nodes. The last node of each path are called leaf nodes or external nodes that do not contain a link or pointer to child nodes. The node having at least a child node is called an internal node. Next one is edge. So edge is a link between any two nodes. It's the height of a node. The height of a node is the number of edges from the node to the deepest leaf, that is the longest path from the node to a leaf node. Next, depth of the node. So depth of a node is the number of edges from the root to the node. So this is the general representation which explains the height and depth of the node. So this is how we calculate the height and depth. So height starts from bottom and depth start from top. Next, why trees? So why we have to go for trees? So tree is some ordering example. With some ordering like example, BST binary search tree provide moderate access or search quicker than linked list and slower than arrays. So trees provide moderate insertion and deletion, that is quicker than arrays and slower than unordered linked list. So like linked list and unlike arrays, trees do not have an upper limit on number of nodes as nodes are linked using pointers. So in order to avoid the wastage of memory or to efficient use of this memory, we go for this trees. So it is a non-linear data structure. So trees applications. So these are the some of the areas where we use this trees. So trees are used to manipulate hierarchical data. So makes the information easy to search and manipulate sorted list of data as a flow for compositing digital images for visual effects. Next, it is used in router algorithms and it is also used for multi-stage decision making. Example, business chess. So this is one of the type of the tree. So binary tree. So binary tree is a non-linear data structure. So tree whose elements have at most two children, that is left and right child, is called as binary tree. Since each element in a binary tree can have only two children, we typically name them left child and right child. So a binary tree node contains the following parts. It contains three parts. First one is data, next pointer to the left child and pointer to the right child. So while we representing this tree as a node, will be represented by using three fields. One is data field, that is next one is pointer to its right child, next is pointer to its left child. So these are some of the types of binary trees. So based on the number of children, we call it as full binary tree, degenerate binary tree, or skewed binary trees. On the basis of completion of levels, we call it as complete binary tree, perfect binary tree, or balanced binary tree. See, on the basis of node values, we call it as binary search tree, AVL tree, red black tree, B tree, B plus tree, and segment tree. So full binary tree. A full binary tree is a special type of binary tree in which every parent node or its internal node has either two or no children. It is also known as proper binary tree. So this is the representation of full binary tree. Next one is degenerate binary tree. So a degenerate or pathological tree is a tree having a single child. It may be either a left child or right child alone. So in that type we call it as degenerate binary tree. Next is skewed binary tree. So skewed binary tree is of two types. It is left skewed tree and right skewed tree. So left skewed tree has only a left child and right skewed tree has only right child. Next is complete binary tree. A complete binary tree is a special type of binary tree where all the levels of the tree are filled completely except the lowest level nodes, which are filled from as left as possible. The last leaf element might not have a right sibling. That is, a complete binary tree does not have to be full binary tree. So a complete binary tree need not be full binary tree. Next is perfect binary tree. So perfect binary tree is a special type of binary tree in which every internal nodes has exactly two child nodes and all the leaf nodes are at the same level. So this is the representation of perfect binary tree. Next is balanced binary tree, binary search tree. So in this binary search tree is most important topic in case of trees. So binary search tree is a data structure used in computer science for organizing and storing data in a sorted manner. So each node in a binary search tree has at most two children, a left child and a right child. See, so the value of the left child is less than the parent node and the value of the right child is greater than the parent node. So this hierarchical structure allows for efficient searching, insertion and deletion operations on the data stored in the tree. So in case in case of linked list, if you want to find an element, we have to search the entire list. But in case of binary search tree, it will compare that the value to be found with the root node. If the value or the key element to be found is less than the root node, then it is enough if we search the left side alone. If that value is greater than the root node, then it is enough to search in the right side alone. So there is no need to search the entire tree.